So today we start lecture 64, and again we continue with our study of simulated annealing, which we will call SA, and this is part 2 of the lecture, and I am Dr. Ranjan Ganguly. Now before we proceed with the description of the method to bring down the temperature from some high initial temperature to a low final temperature, let us look at the philosophy behind the SA method. So here I have drawn a curve which indicates a local minimum point here and a global minimum point here. And if you are using a gradient based method, if you are in any of the region surrounding the local minimum point, then you are going to converge to this local minimum point rapidly. Now, what SA does is that it presumes that you are in this region, and you can see that you must permit the objective function to increase if it has to get out of this particular valley. So that's the particular step which leads to the increase, and hopefully by increasing this you will fall into this region here, and then you can go down and get to this solution here. So that's the basic philosophy of the SA method. So the SA method starts with a high initial temperature, and we call this T0, T subscript 0, and then we slowly reduce this temperature to a final temperature T subscript F. So that exactly is the basic philosophy of this method. Now the details are of course in how you reduce this temperature. So there are a few aspects which are there in this cooling down process. There are essentially 4 components. We saw that 2 of them are the initial temperature T0 and the final temperature Tf. Then there is also the issue of temperature decrement. That means how quickly do you reduce the temperature as you go from the initial temperature to the final temperature. And then beside this, at each temperature, should you perform some search steps, and how many search steps should you perform? So these are some of the questions which are required to actually develop a code for this particular method. So we have seen that if the initial temperature is not sufficiently high, the final solution will remain close to the starting solution, and so you will not be able to capture the global search capabilities of the method. In that situation, the method will not be able to find a global minimum, especially one which lies far away in the design space. The second issue is that when you have a low temperature, the SA method degenerates to a local search method. So there is not much use of this method relative to a local search. So again, you lose some of the potential benefits of the global philosophy of this method. If you use a very high temperature, then of course the good point is that the method can move around in the neighborhood like a random search, and you are capable of going up the hills, you are capable of going down the hills, all the steps are possible. But the problem is you may spend too much time in doing this random search, and this may result in a huge amount of computed time. So this is the problem of using a very high temperature. So a good strategy is to use something like this. A suitable starting temperature could be selected, which leads to a 0.8 probability that a change of design which leads to an increase in the objective function will be permitted. And the value of this temperature can be calculated, and it will depend on the scaling of the function. So for example, one way to estimate this T0 or starting temperature is to conduct an initial search of the design space in which all the increases of the objective function are permitted. Now, if you do this, then what you do is you calculate the mean value of the objective functions, and this we call as del f, let's say strike through f, this symbol here. Then from this equation, T0 is minus del f by log of P0. I can calculate a good estimate of the starting temperature where P0 is taken to be 0.8. Now P0 is 0.8 is a good value to take, but you can take any value between 0.6 to 0.8 as the probability here. Now we turn to the final temperature. So you have started from a temperature T0, which is reasonably high, and now you can decrease the temperature all the way to 0. Now, if you were to do that, the algorithm would take an enormous time to converge. But of course, that is a legitimate choice. Now, the probability of tolerating a worse move, that is a move in which the function f goes up, becomes nearly zero for a low value of temperature Tf. So for very low values of temperature, you are essentially degenerating to a local surge. So what we can do is we can actually use a suitably low temperature as a stopping criteria for this method. One more thing we can consider is that the acceptance of the worst solutions, the probability of this taking place falls below a small probability Pf, can be used to terminate this particular search process. So again, this is some number we can select and we can use it to stop the method. Now we look at the temperature decrement. So this is the amount by which you cool down. So as you go from the initial temperature to the final temperature, you want to slowly reduce the temperature to simulate the actual physical process. So one of the methods which is recommended is the exponential cooling approach. And this formula essentially takes Tk plus 1 is alpha Tk. This is the most common temperature decrement rule. Now typically in this method, we want to have a value of this constant which is close to but smaller than 1. For example, a recommended value is 0.95. But in the literature, values between 0.8 to 0.99 have been used. Now, of course, you would get better results with slower cooling. That means if you use 0.99, you are cooling slower. But of course, the negative side of that would be that the time taken to reduce the temperature to its final value keeps going up. There is a trade-off here. Now, the final issue we need to look at is what to do when the temperature is constant or you are at a given temperature. Now, here one of the simplest choices is to simply do a constant number of runs at each temperature. Now here of course the issue would be how many iterations should you perform at a given temperature for the system to stabilize at that temperature. And this is again a trade-off type of situation, because if you have a large dimensional problem, you may need to perform a lot of iterations for stabilization. So some middle ground needs to be found between stabilization and the need to progress in the temperature decrement. So one of the strategies one can use here is that perform a lower number of runs at higher temperature and perform more runs at lower temperature. So one should remember that the exploration of the local minimum typically takes place at lower temperature, and at higher temperatures you are looking at the design space more globally. Now, one more strategy one can use is that just perform a single run at a given temperature and decrement the temperature very slowly. So one of the equations which is suggested here for a very slow temperature decrease is this equation. Tk plus 1 is Tk by 1 plus beta Tk, where beta is a constant which you can select. It's one of the numerics for the problem. So of course we see that this particular method has a lot of built-in numerics. That's a part of all the heuristic and stochastic type of methods. That is of course the element of randomness here, coming from the random search itself to generate the next point xk plus 1, and also the element of probability which comes into play at this point. So now we are going to end this lecture here, and in the next video I am going to talk about some final comments on this method and how you update the design from xk plus 1 to xk plus 2 to xk plus 3 and so on. I'll see you in my next video.